So I would like to take this opportunity to welcome the presenter. Please, Mr. Attila Barsi, welcome. The floor now is yours to share with us what you have today. Welcome.
Hello everyone, this is Attila Barsi from Holografika. Thank you for this opportunity to let me make this talk on 3D display technologies. I would like to start with explaining what is possible to display. So basically we are using light rays to generate some kind of image for our eyes, and we would like to avoid confusion on what is possible and what is not possible. So we have to adhere to the law of physics as we know them today. And this means that light rays are traveling in a straight line. So stuff that you see in movies, like in Star Wars, is not possible as we know today. So light doesn't make turns in free space. And if R2-D2 is really projecting Princess Leia in the air, then nobody is going to see it who is not in the path of the light rays. And this is also a common mistake on advertising that you see on today's 3D displays, that some of the objects that are being displayed are visible from a viewpoint that they shouldn't be visible from. So if the emitter here is the display screen, then it's impossible for the surfboard to be visible from this angle outside the display screen. So you can be an expert easily on 3D displays by just looking at the image and asking yourself, okay, how many light rays are coming from that display, and how many of those are hitting my eyes? What is the image on them? These are the basic questions that we are going to ask regarding all the 3D displays technologies that we are going to cover today. What are the basic rules for 3D displaying? What is the goal? What would we like to do? We would like to regenerate the window. The window is the perfect 3D display. Whatever we see in it is going to be in perfect 3D. Wherever we are looking, we have infinite resolution image with all the light rays coming through the window's glass and hitting our eyes. We want to somehow reconstruct the light field that is present in the window. If we would just take the window out, and if we would manage to keep all the light beams that are coming through, then we would be done with our work of recreating the perfect 3D display. We are not really concerned about properties of light that do not affect the human visual system. We don't really care about polarization and phase because we simply cannot perceive these properties of the light, but we very much care about the direction, position, intensity, and color of light beams. We would like to have the display do the work and not our brain. If our brain has to do too much work, then it will grow tired very easily. We will see this with the stereoscopic displays. We can encode. So let's check the model for the window. Like, what do we see in the window? We see a bunch of light rays coming from different directions, hitting the window surface with different intensity and color. And we can take this as a general representation for 3D information. We can say that all of these light rays are coming from behind the window. So we can say that our 3D screen is behind the window, and we have a bunch of light rays that are emitted or reflected from the objects within our scene. And some of these light rays are going to hit the surface of our window. And if we take all these light rays, then we can describe them as a parametric function. Then we have described our image, our light field image. We can describe the light field as a function of position with ST parametric surface and direction for each light ray. And then we get a light field function. We can also tackle this in a different way, that if we discretize our light field, then we can say that we have the ST parametric surface and we have an emission range, a field of view, where we have a number of independent beams that we emit from the field of view here. We can also say that if the field of view is fixed and we vary the number of independent beams in the range, then we can define the angular resolution, which will in turn define as our field of depths. So the higher the resolution we have within a certain angle, the more depths we can show without visual artifacts in our light field display. We can define two use cases that are going to be important for us, as the human visual system has two eyes which are located horizontally. It makes sense to speak about horizontal and vertical parallax, because for the 3D to work we need the horizontal parallax, so we need the left view and the right view to be different. And we can also define the vertical parallax, because if we move our head lower or higher, then we can also see a different image on our perfect light field display, the window. We call the display that features both vertical and horizontal parallax full parallax system. But currently, for commercial displays, we usually use horizontal parallax only, horizontal only parallax, to reduce the number of components and the number of beams that we need to emit from the display surface. Okay. This will still provide us with a valid 3D image as long as we don't turn our heads too much. So again, the key component to 3D displaying is directive selective light emission. We want to have a different image, a different light emitted to the left eye and to the right eye. This will depend on where the separation happens. So if the image separation happens on the screen, then the screen surface itself needs to be direction selective. If we separate the images near to the eye, so if we have a glasses-based system, then the separation will be achieved in other ways. We will cover this later. The general approach to glassless 3D displaying is going to be the following. We would like to create a surface that emits or transmits light, where we are able to do this for differently colored light beams for each point. We can control the emission in some way. So let's try to see how many different 3D display technologies we are currently having on the market. Of course, we have the good old stereoscopy, which has a sweet point, viewer dependent view, and usually if we have motion parallax, then it is solved with tracking, which has its own problems, which we will talk about later. We have the multi-view systems, where we have just only a couple of views. and the image is going to be jumpy, so it will have sweet spots. When you stand on the sweet spots, you will have a nice image. Otherwise, you will see either a repeated image or a bad image, a crossed image. It doesn't have a big depth budget, so like the depth that it can display is usually very small, only a few centimeters. We have integral imaging, which is around 16 to 32 images. Usually it's done with 2D panels, and except for time multiplex systems, it's not really nice on the resolution, because it covers the 2D panels resolution with direction selective optical elements, and it simply divides the resolution with the parallax. Okay, we have some types of volumetric systems where we have at least 20 slices and upwards, or time sequential 3D image generation. And we can address the voxels inside the display, and we can color them. It's usually solved with time sequential, so like moving components and projection technology. We have the light field solutions, which are usually horizontal parallax only. But it's also possible to do full parallax on light field display systems. And the nice feature that they have is that they have a continuous parallax, so there are no sweet spots, and the image is valid inside the viewing range, the field of view of the display, from every position. And there are some experimental displays which use holography, but they have very small size, slow updates, and the viewing angle is limited, and they are usually only lab models. Okay, this is the full 3D display technology family tree. We are not going to go into this much detail, but you can check it later. So there are quite a lot of various 3D display technologies. Of course, it always depends on the use case, which is the most acceptable, or which one holds the most advantage for the use case that you target. Okay, let's start with the stereoscopic displays. Of course, you know about this at least a little bit. So the main idea is that for the left eye and the right eye, we need the perfect image, and we add some kind of glasses to provide view separation for the left eye and for the right eye. The first technology that I would like to cover is the active stereoscopy, which is time sequential separation. We show one image to the left eye and one image to the right eye, and while one eye is viewing the image, the other eye gets a black image, so it's shuttered. For this kind of display technology to work, you need a high refresh rate 2D display, and you need some kind of synchronization between the shutter and the display. Usually this is solved with IR transmitters, but I've seen other technology as well. So this was the last big push from the display manufacturers into the 3D world, and this is what you usually can buy in the shops for as a 3D TV. There used to be some solutions from NVIDIA called 3D Vision. They had two versions of this, which integrated into their PC graphics card technology and software ecosystem. And I think it still exists today, but it's not so widespread. The glasses have some kind of active electronics, so they are not so cheap to manufacture, and the image is flickering. It can be very disturbing to the eye, especially if the synchronization is not perfect between the display panel and the glasses. We also have the classic, the wavelength-based separation, which you've probably also seen. Yes, N4 is asking whether the glasses create eye strain for the user. Yes, definitely, especially if the synchronization is not perfect, because then you will see flicker, and the flicker is very stressful for the eyes. Also, the colors are not perfect because of the shutter. So, like for a certain length of time, one image will see black, and it will start the eye adaptation, and then it's very stressful that the eye is trying to adapt to the darker color that you see in half the time for a single eye. Okay. Okay, let's move on to the wavelength-based separation. These are the red, blue, and red, green glasses that you usually get. These are cheap. Usually they have some kind of cheap paper glasses with some color filters. And this is a very old technology that was used in the past to show some special events in 3D and 2D displays. The nice thing about it is that it fits very well into existing chains, existing display chains, and transmission chains, because you don't need additional resolution, you don't need anything, you just separate based on the color in the image. But it perfectly ruins the image colors, so it's not really a nice technology, because even though it shows you the depths of the image, it will not be able to show you the correct colors. Okay. The nicer separation is the wavelength multiplex visualization, where they separate the color wavelengths into discrete spectrums. And the left eye is receiving a different part of the spectrum than the right eye, and this way they can transmit more or less the correct color into your eyes, but still have the 3D image. And this way the two eyes will see the same scene with a slightly different color set, but your brain is more or less sorting it out. You'll see a nicer 3D image. Okay. The nicest one that you can see today in cinemas is the polarization-based separation, where you have polarization filters in the glasses, and the two images are projected through these. And it keeps the polarization of the incoming light intact. So you have a projector that projects for one polarization, another projector that projects for the other polarization on the same screen surface, and the surface is made in a way so that it gives the reflected light with the same polarization, and then it's filtered with the filters in the glasses, so you will have a left view and a right view from the two projectors. And if you have linear polarization, it doesn't work really well, because if you tilt your head a bit, then it will void the eye separation. It will no longer provide you the correct images. Therefore, they are usually using circular polarization to allow for head tilts. Otherwise, you lose the 3D and it becomes very disturbing. This is what you can find in the 3D cinemas. The glasses are relatively cheap because there are no electronics inside, it's just a filter. The colors are more or less left intact. There are some 3D displays that you can buy in the shops that have the same technology, so like passive stereoscopy. But it's not really widespread. There were some from Panasonic, if I remember correctly, that were using passive stereoscopy, but probably other manufacturers also have some flagship displays, or like had them when the 3D TV revolution happened a few years ago. Okay, there are several implementations. The one I've been talking about is using 2 projectors and 2 filters. There are also time sequential solutions where for one image projected you use one filter, for the other you use another filter, but you make it really fast. Swap the filter really fast. You can do the same thing with a half mirror and a micropolymer sheet. So if we want to summarize for the stereoscopic displays, it's a really simple technology. It's a very old technology. It's very cheap to manufacture, and it's very, very widespread. So like most modern LCDs have this 3D feature, but it has a few key problems. It only simulates the binocular parallax. It's missing the motion parallax. So if you move your eyes or tilt your head, then you will not have any parallax. It will not follow the correct camera path. So it will stay always on the original capture path. And there are several unwanted effects here. If you want to achieve motion parallax, then you have to track the user's eyes, and this will introduce some latency. We will talk some more about this if I remember correctly. So the problem with tracking is that it's usually camera-based and image-based, and while you're processing the image, even if the camera has a high frame rate, you introduce some latency, and this is very bad for the eyes. So like your eye is already shifting, but the image is not yet following, and then it will jump to the new location. And while this is happening, your eyes perceive a bad image. It can also be a disadvantage that every user sees the same image. For movies, this might be an advantage because everyone will see the image that the director envisioned. If you want to see some kind of more complex object, and if you want to collaborate on the object, then it's a disadvantage, because if you point out at some key location in your 3D map or in your 3D exploration data, then nobody is going to see the same point, as the image will be distorted to the user's perspective. In theory, it can provide unlimited depths, which is a huge advantage, as the eyes see whatever we want them to see. But in practice, in the cinema, they don't do this, because it would really stress the viewer's eyes if you would change the depths very often, or to extremes, like very close, very far. We can also easily imagine how the stereoscopic images are stored, processed. We have 2 views, which we can either store as color. So we can store the left view and the right view separately. We can have side-by-side and some kind of striped image variations. Some of them are good for processing, some of them are good for transmitting. And we can have the image plus depth format, where we can swap which image we transmit. As you can see, so left, right images are transmitted, and from the depths we can regenerate the other image. Okay, we can have tracked stereoscopy, which is usually done in cave systems or multi-user stereoscopic environments. The problem is that who should we track? So if we have a cable where we project some kind of 3D information on the cable surface, then we can have one user tracked who is driving the presentation, and he will perceive the correct 3D image. But all the others will see the stereoscopy from his viewpoint, and this is a huge problem because the perspective will be screwed, basically. It's like the perspective will not be correct. The other users, and when the user, the driver needs to go to a specific location or needs to have his head moved, then all the other users will experience the same thing, and it will introduce problems with their vision. So they will see it as if the scene moved, and this is generally perceived as a very bad thing. So like it can introduce vertigo effects and stuff like that. So it's not really a nice thing to have a multi-user cave system. We can solve this issue if you have a head-mounted display where you separate yourself from the outside environment and you immerse yourself completely in the virtual environment. In this case, we can track the users individually and render them individual stereoscopic images, which can be very nice, especially if the headgear is not really heavy. Like usually there are two problems with head-mounted displays. One of them is that the gears are heavy, and the other one is that they are usually tethered, so connected to some kind of compute system, and this will reduce the possibilities for movement, and also the detachment from the real world can introduce some problems, like you will lose orientation, you will bump into objects, so like the environment needs to be carefully prepared if you want to immerse yourself in a head-mounted display presented virtual environment. Therefore, some of the head-mounted displays have partial see-through, either by employing cameras that capture the real world and then composite it into the virtual world, or by having a real see-through optical component. And then you will have this problem of how to composite your virtual objects into the real world. Like if you don't measure depths, if you don't have cameras to measure depths, then it's really hard to decide when your virtual object should be occluded, or how it should affect the real environment. So like it's going to be very hard to render shadows and other effects on the virtual world in order for it to match the real world. Okay, let's see some of the problems that are inherent in binocular stereopsis. The problem is going to be this with focusing your eyes on a certain point. So if you have a scene, some kind of scene that you want to view in stereo, then your eyes are constantly moving and trying to find points of interest in the scene, and they are trying to focus on these points of interest to have a better understanding of the layout of the scene and of the important objects in the scene. This is constantly happening in your eye. And while this is happening, your brain is generating some kind of depth impression of the scene from the binocular disparity that is described in this image. And the problem is that when we fixate on a point, then the brain will start interpreting the relative position of all the other points in the scene. When we locate this point of interest, the eyes will start to converge on this point, and the problem is that we need to adjust the optical power of the lens of the eye so that this point becomes focused. Our problem is that these two things, like finding the point of interest and then focusing on it, are reflexively linked. So we cannot change this behavior easily. And when we have the stereoscopic 3D viewing, where the focus will not change, the focal point will not change, the focal point of the rendering or the displaying will not change, this is very disturbing. The eyes will focus on the screen no matter where the object is projected. So even though the object is very far away, our eyes are just going to focus on the screen, but they are converged on the object. And this is a major reason for the visual discomfort. It's called the convergence accommodation mismatch or problem. And this is what will introduce most of the health effects that are commonly associated with the stereoscopic viewing. This will introduce quite large visual fatigue. This is why most of the people cannot watch a stereoscopic presentation for more than 10-20 minutes. There are some other depth cues that we rely on that will help with this problem. If we have motion parallax, that means that when we move, we see objects from different perspective, different angle. And this helps our brain to interpret and understand what is in the 3D space. We rely on two main visual cues: the slightly different image that we see when we move our heads or our eyes, and the way the shape changes when we move. So like the perspective distortions that happen when we move our head. For this to work, we need to have some kind of positional information, and then we need some kind of motion parallax that we introduce by updating the stereoscopic image based on the movement of our eyes and our head. When the brain starts seeing the scene in 3D, that means when we introduce the stereoscopy, then the brain starts to tell the eyes and the head to start these micro head movements to check if the 3D model in the head is in the brain matches the real 3D model. So when it perceives some kind of discrepancy between these two, and it sees that the 3D world is mismatching the expected one, then the brain will start to work around this problem. It will start guessing what the actual shape of the 3D object would be. And this introduces some kind of fatigue in the brain. So we are working very hard to find out why our vision is not working correctly anymore. And this will introduce these kind of vertigo and health effects that we were talking about. So let's move on to the next topic. When we are not really satisfied stereoscopic displays. We've seen that there are lots of artifacts and lots of health issues. So we need to step up our game and move to the autostereoscopic displays. And we can give a nice definition for what an autostereoscopic display is. An autostereoscopic display is simply a display that you can look at without additional headgear or special glasses, and it will still provide you a nice left-right image. It can use various technologies to do this, like marketing department in various companies call this glasses-free 3D, naked eyes 3D, natural 3D, and so on and so forth. We know that these displays usually have some kind of specific depth budget, so they cannot do the same thing as stereoscopy because like they have some kind of optical component to separate the images. And as the users are not tracked here, or like usually are not tracked here, we cannot provide them a perfect image. We need to have some kind of images that cover the viewing range, and we don't really know where the user will focus. So we will try to display the depth range that fits the display optics well, rather than the scene's depths. Okay, how do we do this? How do we show 3D without glasses? we will use some kind of clever optics to put the left and the right images to the correct location. If we can do this, we can separate the space in front of the screen into viewing zones, where we have some kind of optimal viewing distance, where the projected image will happen to be in the correct position for the eyes. We will see some technologies that can do this, that can separate these images and project them to certain positions to have the correct stereoscopy in front of the display. One of these is the parallax barrier display, which has an array of slits spaced in front of a high-resolution display panel. This will cause each eye to view only light passing through alternate image columns. These are typically stereoscopic display. I mean, they only have two views, and they are implemented usually over flat screen LCD displays. In all the mobile 3D devices that you've probably seen, from Nintendo 3DS to LG Optimus, this is the go-to technology for the mobile handheld system developers for 3D displaying, because it's like, from the optical point of view, it's relatively easy, and it fits very well to existing handheld display technology. There are also some manufacturers who do the same for monitors, like Fidelity, Sharp Master Image, and so on and so forth. The nice advantage of this technology is that for the light rays, they will not suffer any kind of distortion. So like they will really go into the eye without hitting additional optical components. Which is not true for the next one, the lenticular lens-based displays, which has the following property. It has some lenticular lenslets covering the same kind of high-resolution LCD flat-screen display, and these lenslets will provide the different viewing direction for the different pixels. So the focal point of the lens hits a different LCD image plane, and this will provide a nice image for the left eye and for the right eye on the specified image planes. So like if you generate an image for one of the image planes of the LCD and left image and the right image for the other image plane, then they will go directly through the lenslet and into the left and the right eye. This is very, very widespread, so like there are lots of manufacturers who do this. You have to know the special pixel arrangement on the underlying panel. There are several variations of this. The arrangement is usually kept secret because like it's a manufacturing secret. And then you have to design and manufacture the lenticular lenslet and just simply put it on the screen to have the correct image. So this is the basic solution. There are two ways to do this. One of them is to generate the views and scramble them. So like make the RGB subpixel panel pattern on the original image, and then the lenslets will unscramble the image for your eyes. This is what is done by Oleoscopy, Fidelity, NewSight, and many other manufacturers. And there is another way where the display expects some kind of image plus depth-based video or content, and then it will automatically generate the missing images from the image plus depth representation internally. So for the multi-view displays, we can summarize that they are relatively simple. The design can be very complex for the lenslets and for the parallax barrier, but it's easy to manufacture once the design is complete. And usually that they say that this is the next step after stereoscopy, but it has quite a few problems. It has a limited depth budget. Even though it has a wide display field of view, the content field of view is very narrow, so like you can only view the content correctly in sweet spots, and over the field of view it has lots and lots of places where the content is either repeated or jumping back, so it's not really possible to move in front of the display and perceive the correct image. It can provide horizontal motion parallax, but it has invalid zones between two valid viewing points. It's mostly used as a marketing tool today, but it's a question whether it is okay for a marketing tool to be visible only from certain set points. This is questionable. Usually the effective resolution is the panel resolution divided by the number of views. When the optics is fixed, this is the case of the classical lenticular display. You cannot use this display as a 2D display because you will have some strange patterns on the image due to the lenslets, and you cannot use the resolution that is covered by the lenslets. You have to use the one single directions resolution to display a 2D image. There are some ideas on how to fix this. You can have switchable lenticulars. You can use horizontally double density pixel architecture to provide the same 2D resolution for the display. You can also use integral imaging, where you have some kind of elemental images on the display panel that goes through lens arrays, and then you can have some kind of integrated image in front of the display. You can imagine this as fly eye lenses. These deflect the light beams from each underlying pixel to the given direction, addressing spatial points. So this means that you have a small area on the display where you have some kind of lens array, and the individual pixels in this structure are deflected to a certain direction. And if you take these small areas and select one position from each of them, then you will have some kind of small elemental image that can be considered as one pinhole camera image. This is a good 3D reconstruction. It has full parallax as the areas is covered by lenses that are also providing vertical parallax. It's an easy approach, but the capture is a bit hard, as you have to reverse the geometry for the acquisition. The downside of it is that it has a very narrow viewing angle, and you need to have very high resolution in the display panel in order to provide a nice resolution for the elemental images. So here are some of the examples that are using this technology. As you can see, if you want to provide a nice image, then you need super high resolution. Okay, you can solve this issue of resolution with time multiplexing systems, where you have the same resolution as you would normally have in a 2D display system, but you have very high refresh rates, and you use the refresh rate to provide additional pixels, to introduce additional pixels into the system. So imagine that you have a 180 Hertz display, then you can introduce 3 more views, or like if you have 120 Hertz, then you can introduce the stereoscopy. You can introduce 2 views at 60 Hertz. If you manage to deflect the image into the left eye and to the right eye. You can have this technology with layered display that is shown here, where you have the image on the back plane and you have some kind of shutter-based front plane which will deflect the images to the left eye and to the right eye. You can also introduce volumetric display, where you have the media positioned or moved in space. This is like looking into the crystal ball. So imagine, like, the easiest way to explain this is that you have a rotating mirror that will deflect the image to various viewing directions. And you have a projector, a very high-speed projector, projecting the image onto this mirror, and then you will have a 360-degree walkthrough or walk around for your scene. Of course, you cannot cover the projector, so but otherwise this works. But the problem is that for this to work, you need some kind of screen that can solve the occlusion problem. This is a very hard problem to solve. As you can see, that the object that is visible is sort of see-through. So, like, you can see the real world behind it. Sometimes this is a problem, sometimes it's not a problem. And the other problem is that you need a very high bandwidth to provide the image for the high-speed projector. Usually they solve this by going into grayscale, with some kind of low bit depths. It can even be simple black or white, like in the case of this USC holographic display. So simply they take the 24-bit image and they subdivide it into 12 black and white parts where they only have a single bit, 2 bits of color, some small grays. That's it. Okay, you can have rotating LEDs. This is the same thing, but it's emitted, not projected. And if you really want to do Star Wars, then you can do plasma. So you can focus infrared lasers into the air, and this way you can emit. You can have an emitter on a certain voxel in space. But like this technology uses high energy and it's quite dangerous. So I wouldn't recommend it for home use. Okay, there are some volumetric displays which have multiple planes with multiplanar optical. They are working with a multiplanar optical element and high-speed projectors. Either they are like they are using LCD plus transparent LCD, and this way they are projecting images into the individual optical elements, and this is what you see when you display. Either you can do this with a depth resolution of 2, where you have a front plane and a back plane, or you can have these multiplanar optical elements, and then you can provide a higher depth resolution. If we want to summarize volumetric displays, they are excellent in providing true look-around capability. So, like, you can move around freely, and you can look at the scene from different angles. But it's using moving parts, which is always a problem because they break down easily. The volume is usually very limited, so you cannot make this very big. Imagine if you would have a rotating, like a 1 meter by 1 meter rotating component would be very hard to move. You need a big motor and so on and so forth. They require very high-speed imaging components, which will introduce flicker in most of the cases. It will not have this problem of convergence accommodation conflict, because the 3D points will really originate from the spatial points that you perceive them, where you perceive them, sorry. So there was a question of what would we classify this this display? I think this is not volumetric, not holographic. It's a Pepper's Ghost or something similar. So, like, it's just projected 2D. It's not a real 3D display. You just project something from the smartphone to the side of this plastic. So it's not a hologram. They just, yeah. It's not real 3D, so you will not see it in 3D. That's the problem. It's a projected 2D image. It's a Pepper's Ghost. Okay. Anyway. Okay, so for volumetric displays, the occlusion can be a problem. Usually it's like either translucent or wireframe only, because there are no occluders in the optics. So like one point cannot occlude the other. And the image generation can be a problem. It needs to be very high speed if it's a time multiplex system, so that's why they sometimes employ compression, like color compression or something like that, or some kind of lossy compression to be able to supply the image generator or the projector with images. Let's also check what the holographic displays do. Holography will store and reproduce the properties of light waves, all the properties, even the ones that we are not interested in. They are using acousto-optic material, and they have spatial light modulators that they can address optically. It will generate the pure holographic pattern. But even if you have very, very high resolution imagers, it's still constrained because it needs so much information inside the viewing range. It has a limited angle, a small viewing box, and the calculation load is very heavy. It needs a really high resolution to work well. It has a very good 3D image quality, but usually the content is static due to the high computational time that you need to generate all the necessary patterns. It is going to be the ultimate technology, so like a hologram is the best 3D image that you can get, but it's not practical today to manufacture a holographic display. There are several experiments, laboratory experiments that deal with holographic displaying. I think so like these technologies need much more research to become commercially feasible. Like this is the one that on the floor was showing us. So like it's always like these solutions are advertised as holographic, but they are not holographic. So they are just a simple half reflecting, half transmitting glass. So like you project something onto a glass that is reflecting it, and then you will see an image on it. Like if you project a good image, like a black background and some kind of object in the foreground, then what you're going to see is the real background behind the optical element and the image reflected from the optical element. And this is what we call Pepper's ghost, because it's from an old magician's trick. Okay. You can also have 2D projection on various half-transparent films or a Fox screen that looks like a floating image in the air, but it's just somehow a projected 2D image, so it doesn't have stereoscopic depths. Okay, let's try to cover light field displays. This is what we are mainly producing and selling. Currently, there is only one real light field display that is manufactured as a real product, which is the HoloVizio by Holografika. We have optical modules in a projection-based technology, where the optical modules are projecting images onto a holographic screen, and the holographic screen has a direction selective property that we have discussed in the beginning, that it will let through differently colored light beams to different directions through the screen. And this is what we call a voxel. Like one voxel is where the light rays from the optical modules meet in a single point. We reconstruct the light field of an image instead of 2D views. So in the system there are no 2D views at all. We reconstruct the emission or reflection on the scene based on the actual light ray directions of the optical modules' light rays. The emission angle is geometrically determined. That means that the placement of the optical modules on the holographic screen will determine where the rays are going to come out of the holographic screen and hit the user's eyes. And the projected module images, like the images for the optical modules, are not 2D views. So there are no pinhole cameras anywhere in the mathematics that describe how to render a correct light field image. As you can see, for a single view or a single point, the light rays that describe that point are coming from multiple optical modules. We have continuous motion parallax. That means that you can move freely around, freely inside the field of view of the display. You don't have any kind of discrete borders between views. There are no jumps here. You can freely move around. We have several types of HoloVizio displays. We have a 72-inch large-scale 50 megapixel light field display where we have a high angle resolution, which is 0.9 degrees. But as you can see, we are also struggling with the 2D equivalent image resolution, which is HD for now for these kind of systems. And we have a cluster that renders the images for the light field display. We also have smaller ones, digital signage or kiosk-like applications, where we have an even lower resolution, but for these kind of applications it's sufficient. You can see that this is also a cluster-based system. And we have a nice front projection system where we placed the optical modules in front of a reflective surface. So like instead of the arrangement that we had before that we are projecting from behind, which took quite a lot of physical space, now we are projecting from the front as you usually do in the cinema environment. And this way we can place the users in front of the holographic screen. Okay. Unfortunately for us, the screen technology is a bit more sensitive to damage. The other technology can be easily protected. This one can be damaged easier. So we recommend these kind of arrangements for cinema-like environments where the users will not be able to get close to the screen. Okay, this is the final product that we have, which has a 140-inch large reflective holo screen. We covered the screen with 63 megapixels, and we have LED-based colors, so it has a very nice image. Peter has explained, or Subaredi has explained this already. It has an exceptional brightness, narrow field of view compared to our other solutions, but this has been designed for cinema environments where this is quite sufficient. We don't have any perspective distortion. It's 2D compatible, so like without switching, you can display 2D films on it. So it fits a cinema very well. Okay. What I would like to state, or what I would like you to think about, is whether the glasses-based systems are good enough for home use. I would think not really. So if you need some additional tech or additional equipment just to watch TV, then you will have like these problems of how many do you have at home. Like if you have a party with 100 guests, then you would need 100 glasses just to watch TV, or like even if there are only 10 people, then this becomes a problem, and like you have to keep track of them, like where are they, where did I put it, and so on and so forth. And you need to be, and if you need to be in a sweet spot, then this is not really nice. So like you have to arrange your living room in order to find the sweet spots for the display. This is not really a nice thing. So I would hazard that the glasses-based 3D display technologies are not going to be comfortable enough to use at home. And I think I'm right, because I've seen that the adoption of the 3D displays that we have currently on the market has not been really good. And I think the big push for the stereoscopic 3D displays is not really happening anymore. Okay, this is just some information on how this technology will limit the growth for 3D displaying. This is probably not so important for you, but you have to be aware that the glasses-based stereoscopy is not going to be adopted so much anymore, as I think that the big manufacturers are going to remove this technology from their current generation of displays. And I think the future is for glassless stereoscopy, so some kind of glassless stereoscopy, and I really hope that it will involve light field displays in some kind of way or forms. Okay, thank you everyone for listening, and if you have questions, I would be happy to answer them. And my colleague Zsolt, who is working on display optics especially, is also available for comments if you have any questions. Okay, thank you very much again for listening. Okay, no questions? Okay, Alex, how about we wait for like 5 more minutes, and if no one has any questions, then I think we can conclude for today. Okay, while you're thinking about questions, just a quick question from my side. So like the next big 3D technology seems to be virtual reality and augmented reality displays, like HoloLens from Microsoft and Oculus Rift from from Facebook and or from Oculus and so on and so forth. Did anyone ever use such a display before? Do you think it's a good solution to 3D displaying? Maybe you've seen the Samsung Gear or like one of the VR equipments that needs a smartphone to work, or the cardboard from Google, maybe. Okay, so Anna Flores used VR HMD displays before, and she thinks that they are not so good. I think the same thing. So there are many challenges to overcome for the VR displays, especially the tracking. So if they have some kind of tracking, and the optical tracking systems are like, they have really high latency. So like maybe if they would use better tracking, that would also be like more expensive, but maybe faster, then I think they could get a bit better. And also the problem of filming and content generation is like not really solved. From the virtual world side, it's pretty good, but from the real content, it's, I think, not really so nice. Okay, I don't really see any other questions, so from my side, I will be available for questions via email or Skype if you have anything additional that you forgot to ask. And I would like you to thank again for all participants. And I think Peter is okay. Thank you, Peter. Okay, thank you very much, everyone. Okay, so I think I will take my leave now. Thank you, everyone, for attending. Yes, yes, you may publish it on the YouTube channel. Okay, thank you. Bye bye.